Good afternoon, Penn Staters, and thank you for joining us. I'm Paul Clifford, CEO of the Penn State Alumni Association, and I'd like to welcome everybody to today's virtual speaker session. Today we welcome Professor José Duarte, and today's discussion is the latest installment of a recurring series of virtual programming that the Alumni Association is bringing to the Penn State community. We'll be speaking with experts, university leaders, and other Penn Staters who will share their insights and perspective with you in the coming weeks and months. Additionally, the Alumni Association offers online networking events, career programs, and webinars, and you can view the full list of all of our events that we offer at alumni.psu.edu/events. Now I'm happy to welcome José Duarte, who is a professor of architecture and landscape architecture in the Penn State College of Arts and Architecture, where he holds the chair in design innovation and directs the Stuckman Center for Design Computing. He is also an affiliate professor of architectural engineering and engineering design at the Penn State College of Engineering. The world is experiencing significant growth in population and fast urbanization at such a scale that we will need to build over the next 20 years as many houses as we have built in the past 2,000 years. I'm going to say that again. We will have to build over the next 20 years as many houses as we have built over the past 2,000 years. His talk today will describe how innovative design and construction technologies developed to overcome this situation on Earth were used to design a habitat to support human exploration of Mars. Professor Duarte will also show how lessons learned from his Martian efforts may impact the way we design and build cities on Earth, making them more resilient, including to pandemic threats like COVID-19. Professor Duarte, thanks for joining us.
Thank you very much. Good afternoon, everybody. I'm going to start sharing my screen. So can you see the screen now?
Yes, we can see it.
Okay, very good. I'm going to switch into presentation mode. First of all, thank you very much for this very kind invitation. It's my pleasure to be making this presentation and show the work of my colleagues and myself in the Additive Construction Lab. As Paul said, I direct the Stuckman Center for Design Computing, and I have been involved with a multidisciplinary team to develop houses for Mars, which I'll talk about in my presentation today. So, but let me give you first a little bit overview of the context. So the center has as its mission to support the integration of digital technologies in design and construction. But the focus is not on technology, but on strategically deploying technology to address contemporary societal issues. So the goal is to contribute for the achievement of the United Nations Sustainable Development Goals, which you can see on the slide. And what does motivate our research? As Paul mentioned in the introduction, if you look at the graph showing the growth of human population, we'll see that over the next 20 years, we will need to build as many houses as we have built in the past 2,000 years. This is a huge problem of a huge scale. And the message is, even if we are dealing with computers and computation, the research is socially motivated. So what you see now is different approaches to the problem. On the upper left corner, you see what people do when they cannot afford to buy a house on the market. They basically build the houses themselves, and they create these environments, which we call informal settlements, because they were not planned. And they have many qualities, but also many flaws. One of them is the lack of infrastructure and public spaces. On the right-hand side, you see the traditional governmental approach, the use of mass production to produce many houses in a short period of time. But like the informal settlements, they also have problems. And some of them are actually social problems. So that's not a good answer to the problem. So what we would like to have is actually what you see at the bottom on the left side, which is that we would like to build settlements with the qualities that we perceive and value in the settlements that grew incrementally over time. So what is the solution? How can we design environments that have the richness and work well like these historical settlements that become very often touristic attractions? So this slide shows the DNA code, which is the code of life. And the idea is if you tweak the code a little bit, you end up with a different living creature. And the idea is that this does not happen randomly. It happens in a way that the creatures evolve to become the fittest to the environment when they leave. So this is the idea that we want to bring into architecture. The code to generate buildings that are the fittest for the environment where they are built. So it just happens that this is not new. If you look back into the history of architecture, you see books that were written, some of them thousands of years ago, where people describe very rigorously how to design buildings. And this is done in such a way that it's more or less straightforward to convert the instructions that you see on these books into computer programs that are able to generate 3D models of a building. So what you see on the screen is actually the output of a computer program that some of my students wrote a few years ago that converts a famous book on architecture, written by Vitruvius, a famous Roman architect 2,000 years ago. And he has one chapter in the book that describes how to design Roman theaters. So what the computer program does is if you specify the number of spectators, it will generate in a matter of seconds a 3D model of a theater according to Roman rules for that number of spectators, for 5,000 and for 15,000, for instance. And so what we have a computer program that is able to generate customized designs. And then what we do is use digital fabrication, or in this case, at this scale, rapid prototyping, to very quickly produce a 3D physical model of the output of the computer program. So this is basically what we are advocating to use to solve the problem of building many houses in a short period of time and customize so that they satisfy the requirements of their users. So the problem actually requires two systems for the solution: a design system that takes information about the context and outputs a design solution, and then a production system, as we'll see. And the idea is that we use computers, the high processing power of computers, to very quickly, process data about the site and generate data about the solution. So if you look more closely into the design system, you see they have the ability to interpret the context and generate a design brief. So we have a system for doing that. We have another system that's able to generate candidate solutions. And then you have a system that's able to rate and rank those solutions. So the idea is that we use search and optimization to find the optimal solution for a particular context. So in terms of the design of housing, this means the ability to design houses by people. So what you see on the screen is actually an interface that we developed at the center a few years ago, in which you have an interactive tabletop that anyone can use to design their own house, their own customized house. The interface can be developed in many ways. For instance, in this case, what you see is actually another type of interface that runs on the web. So like a virtual architect that asks you questions and will generate a house. So with these systems, you are able to generate customized houses. For instance, this particular system has the ability to generate 67 million different houses. This means that you can actually create very diverse environments. So you have some of the qualities that you value in informal settlements, but at the same time, you can guarantee that they will have infrastructure and public spaces. So once you have the ability to generate customized solutions, you need also tools to materialize those solutions. So you need a production system. And the idea is to use digital fabrication and digital construction to very quickly, in a very efficient and rigorous way, to materialize those solutions. So these systems can take at least two forms. In one, you have what we call a kit of parts. You produce the standard components and you combine them in different ways and they are assembled to make the house. There's another more modern solution to actually use additive construction to very quickly print the building, as we will see. So these are the two paradigms, the kit of parts, and the idea is that you combine standard components into different houses in different ways. And the other one is actually to use a robot to print the house, so large scale 3D printing. And that's basically what we have been developing. So this is quite interesting because you can use this strategy on many different scales to design the house, to design the urban environment, but also to design the materials. For instance, in this particular case, you see a system that we have developed to design what we call a functionally graded concrete. If you look at human bones, their density is not homogeneous. They are denser when they need to be stronger. So this is the idea that we use to develop a customized building component. So for instance, concrete has a binder, which usually is cement, and has aggregates that usually is sand. But you can replace part of the sand by a lightweight aggregate, and therefore you can change the properties of the building component. So it can be stronger and heavier when it needs to be stronger, or it can be lighter and have higher thermal insulating properties. So what you see in this image is actually a customized wall. You see it's denser where the loads are stronger and lighter where they are smaller. And then we develop the system to be able to materialize this. So what you see here in the image, in this animation, is actually the printing of functionally graded concrete. So the concrete that's being printed is not homogeneous. It does not have the same composition. So the composition of the concrete on each point is customized so that it actually performs its function as best as possible. So the part that you see here, as on one side, it's 100% sand as aggregate. On the other one, part of this sand was replaced by cork granules. So and then you can design a customized material as well. So another colleague of mine called Shadi Nazarian developed the ability to transition seamlessly between concrete and glass. This means that you can actually have windows without frames. So you simplify construction. You decrease the number of trades that are required to build a building. You decrease the cost and efficiency. But printing in concrete is a very complex endeavor. There are many different variables associated with different parts of the system. You have variables that are connected to the environment, like the air temperature, humidity, and so on. You have variables that are connected to the composition of the concrete that we are using. And then their properties like viscosity, flowability, setting time, and so on. And then you have variables that are connected to the printing system. For instance, how fast you print, what's the size of the nozzle to print the concrete, and things like this. And because the material and the printing system constrain what you can do, you have variables associated with the design. So the printing system constrains design, but at the same time, it allows you to print buildings without formwork, concrete buildings without formwork, which makes construction a lot cheaper and faster. So there are many advantages in doing that. So part of our efforts is actually to find the correlation between these different variables. But because when we don't get it right, see what happens. Everything seems to be going well, and all of a sudden, it just collapses. So we need to learn, so we need to understand, we need to model the system, the different variables of the system, so that you know if we have this material with these properties, what should be the printing settings, what should be the design constraints, and so on. So this is exactly what I've been doing at the Additive Construction Lab. We are developing different concrete mixes that are printable, that can be used for 3D printing. We are developing the printing system that can take different configurations. And we are also understanding how material behaves once printed, because concrete is not like plastic that hardens very fast. Concrete takes some time. So when it's deposited, it deforms. So we need to model this deformation so that we end up with a part with the design that we wanted. So we need to compensate for material deformation to get an accurate shape. This is another stream of research. And then you need to make sure that concrete has the right strength, that will not collapse during printing and after printing. And then we need also to develop, the ability to make it completely sealed. We need to develop the ability to incorporate, openings, like we see in this case. Another robot it's being used to place the window frame during printing. We need the ability to introduce reinforcement and make sure that the concrete can endure successive freeze-thaw cycles. We also need to understand which kind of shapes can be 3D printed without formwork, because this does not work with any shape. So there's a correlation between the features of the system and the design and the features of the design. But what you can do is a lot. The class of shapes, the variety of shapes is actually very large. So this is also what we are trying to understand. What are the forms? How can we best take advantage of the printing system in concrete to make buildings? And we want to, we are developing the technology to do this to avoid formwork, just to make construction simpler and faster. So what you see in this case, actually, it's a dome shape, a fully enclosed structure that was, built, designed and built by one of the students of the class that we teach about the technology. And if you look back into vernacular architecture, the architecture that was built by people over time, you see that they had to deal with similar constraints. And that what we're trying to understand is to learn from history, is find out which kind of shapes we can build and design. And because we are talking about moving to different places, we also need to be concerned with logistics, how to pack the system, how to actually set it up on site so it actually works in an efficient way. So a few years ago and last year, we participated in a NASA competition whose goal was to design houses for Mars that were 3D printed. And it had actually two parallel streams in the competition. In one, we had to design the system for Mars. In the other one, we had actually to use the same system to build on Earth. So what did we do? We developed a platform that uses BIM. BIM is a standard of the industry. It's called Building Information Modeling. And there are software that are built according to these standards. So our system has the ability to generate different solutions, like I mentioned at the beginning, and we are using parametric design for doing that. Then we need to check the performance of the solutions from different viewpoints: structural viewpoint, an environmental viewpoint, and the constructability viewpoint. And then we need a system to find what's the optimal solution for the context, the one that works better. And then, because we need to articulate the work of different robots, we need to do the construction simulation to make sure that they don't collide while printing and things like this. So what you see here in this slide is actually the system that showing how you can use parametric design to design shapes, to design different configurations for the shelter. So we developed a design system that's based on modules, and those modules incorporate the rules of 3D printing. So the constraints are imposed by the printing system and the material that we're using for printing. And that limits what we can do, but it's still a very large range of possible solutions. So you can get the solution, and then you can check for the performance of the solution from the structural viewpoint, from the environmental viewpoint, or from the constructability viewpoint. And then you can use optimization to actually find the optimal solution. So what you see in this animation is a system at work. So it goes through different cycles. It generates different candidate solutions. It checks them, it evolves to the next stage until it finds a solution that's the best for the particular context. Because we are using the same platform to design for two totally different environments, as you can guess, the outcome for Earth is different from the outcome for Mars. So the same system generates different buildings because gravity, atmospheric pressure, and so on are different on the two planets. For instance, on Mars, the gravity is much lower, so we actually need to be more concerned with lateral loads because the structure needs to be pressurized than on Earth, when the vertical loads are more important. So thus the different shapes of the buildings. So what you see now in this animation is actually the simulation of the setup because to qualify for the final stage of the competition, we had to show that we could print. And this is the animation that we submitted to show how we were thinking about printing the structure on the site. And there were constraints like the maximum area that we could occupy. So what you see here is actually the printing system. And what we are doing now is together, developing a product that can be used by the industry that, benefits from the research that we developed for the NASA competition. So you see, the simulation of the setup, and now you see a simulation of the building being printed before the actual competition. So this was done for the virtual competition. And you see that the second robot will place the windows at some points. I think it's going to happen now, as you can see, and then it continues printing. So this is actually a film of the actual competition with our structure being built. It was a thrill to see the structure that we've been dreaming about for several years actually being printed. And it worked. So we were able to print the first fully enclosed 3D printed structure. So this is an image of the site a few moments before it finished printing. And this is actually an image of the team celebrating, the success at the competition. You see, some of my colleagues, Sven Bilen, Shadi Nazarian, Ali Memari, Randall Bach, Alexander Radlinska, Nick Meisel. So it's a team of 7 faculty and many graduate students who are working together. And they embody what I think is the spirit of Penn State, multidisciplinarity, working collaboratively to develop products that no one alone could develop. And because at the end, it needs to resist. So you need to develop something that's resilient, that can resist the forces during its use. So how can we learn from these efforts and design more resilient cities? So we know that we are going through what we call a pandemic. And if you look at data, you see that the disease did not spread at the same rate on all the places. So there are cities when it's actually spread faster. So what we are doing now is actually to analyze how the disease spread in these cities to find a correlation between the urban features, and urban features might be the density, the public transportation patterns, might be the shape of the buildings and how they are organized, how the street grid works, the walkability, so on. So find the correlation between city features and patterns of the spread of the disease. And what we want to do next is actually to learn the correlation and find out what's the best design to prevent that diseases spread very fast. So we want to use this information to design cities with more adequate features, more resilient cities. Thank you very much for your attention. I'm now open for questions. Thank you.
Excellent, Professor Duarte. Thank you so much for your presentation today. We have a couple questions that are coming in here. But let me start off first with talk a little bit about how did you become interested in this research area, and in which ways has Penn State positioned you to be successful?
So I became interested in the housing problem many years ago, when I was in college. I'm originally from Portugal, and at that time, this was in the early 80s. Portugal had a housing shortage. So when I was going to school every day, I had to cross different parts of the city. So in the outskirts, I would see informal settlements, and then I would see mass-produced houses, and I would get to the city center where the university was, which was beautiful. So I wanted to understand more and see how we could develop solutions so that people could live in the environments as nice as the city center. This is how I became interested. Penn State was in my career, a key role, because before coming to Penn State, I had worked on developing the design system, the ability to design systems, how buildings that are customized for the environment. But it was at Penn State I was able to develop the technology together with my colleagues to materialize the output of the design system. So to be able to 3D print buildings in concrete. And I think this was possible at Penn State because Penn State places a big emphasis on collaboration, on multidisciplinary research. Everything is in place to foster such kind of collaborations.
So when you got interested in the housing problem, talk about Earth's capacity to support 2,000, the same number of dwellings over the next 20 years that were built in the previous 2,000 years.
Right. I mean, you see, the scale of the problem is such, and sometimes you don't realize the scale of the problem. You need to actually step back and look at these graphs to see, what the problem is. You need new approaches. You need to find ways to be able to build in such a short time the same amount of houses that it took, decades, centuries, millennia to build. And obviously, there's a limit. This can't go on forever. So I think, I believe that the planet would auto-regulate itself at some point. And you can see, for instance, in the Northern Hemisphere, the population is not growing as fast as before. It's actually decreasing in some countries. Right. But it's still going very fast in the Southern Hemisphere. So I think at some point it will level, so it will reach a plateau. And maybe that's when we start colonizing other planets like Mars.
Yeah. So how does the automation of this process impact the workforce? Obviously, there is a human element in the design and developing everything before it gets to the 3D printer. But what does it do for the construction industry in terms of how the workforce needs to shift?
Right. So I think, it shifts many things. It shifts the design process. So instead of having one architect, for instance, designing one house, we actually have an architect designing a system that can, design many different houses. So it the changes start at the top, at the design level. And then it's going to change how you make the building. So you need, a construction workforce with a different set of skills. They don't have to carry buckets of concrete anymore. They need to learn how to operate machines. So I think, society is getting more sophisticated. But that's the way it is. And obviously, Some people have asked me in the past whether this will drive people out of work. I don't think so. It's just going to change over time the way we work. So we will start working in different ways.
That's the answer with all technology, right? Technology does eliminate some jobs, but the workforce and the market respond to that in terms of other jobs that are then created because of the new technology. So it's the natural force of the market in play.
Yeah, so I think the ethical part of this is actually quite important. So like in anything else, you need to weigh the advantages and disadvantages. In this case, I think the advantages, largely overcome the disadvantages, because if we are able to provide people with a decent home, everybody with a decent home, I think that's a great accomplishment and justifies the use of these means.
Yeah. You talked earlier in your presentation about the different materials that were experimented with and that you're using to develop that can be 3D printed with various mixtures of concrete. I don't know a lot about construction, but I do know that when they're using traditional concrete, they usually reinforce it with rebar. Are the materials that you are putting into this, are there applications for that outside of use with 3D printers? Might they replace the need? Do they make concrete stronger? Might they replace the need for rebar?
Yeah, so that's a great question. So we have actually different streams of research. In one case, we are developing structures that work under compression, so the need for reinforcement is minimal. In those cases, you can use reinforcement like fibers, small fibers, that you mix with the cement and the aggregates to give the structure some tensile abilities. On the other hand, we're actually developing the technology to place the reinforcements while printing the concrete. So we have these two parallel streams of research going on.
Great. A question coming in from the audience. They want to know, how do you change the feed from heavier to lighter materials during the print? So
there's also a very a good question. So what we do in this case, you have two different pumps. In one, we have the concrete with the sand as the aggregate. In the other one, we have the concrete with the cork granules as the aggregate. And by changing the relative speed of each pump, we can actually change the gradient. So if we pump faster with the machine that has a larger amount of sand, the concrete that will be output will have a larger amount of sand and so on. So it's by playing with the speed.
So which companies are actually producing and manufacturing the 3D printers of the size necessary to accomplish this task? And what is the likelihood or how far into the future is it when 3D printing of structures actually becomes the construction standard?
I think we are still a few years away from that situation, but there are already companies on the market that actually 3D printing houses. And we are actually, using the results of our research to create a startup company to take advantage of the printing system and the materials that we have developed, and take advantage of our design skills, because we have to learn how to design for 3D printing. So we hope, let's say, in 10 years, I would say this will become a standard, but I will have a significant amount of buildings that will be 3D printed.
You mentioned about how how one of the applications for this is living on other planets. So how do you create the environment here to simulate life on Mars, right? To simulate the gravity, all the things that you talked about that that you have to account for. How do you simulate that here on Earth?
Okay. So I have a colleague on our team. Her name is Alexandra Radlinska, and she has been doing experiments at the International Space Station. She sent some concrete samples to the station, and they were actually, mixing the concrete up there to see how concrete behaves in the absence of gravity. So we are doing that at the same time. the computer is a machine that simulates any machine. So we're basically using the computer to simulate, the conditions on Mars. So the platform that I've described does exactly that. So, to a certain extent, we can predict what's going to happen, and then obviously need to validate, what our model is predicting with, some actual examples. So what we did, because we have this platform to design for Mars and for Earth, and it generate two different structures, suitable for each environment, and it worked for Earth. So my expectation is that it would work for Mars as well. Obviously, Mars, it's a very harsh environment, and in some cases, you can simulate the conditions on Mars, on Earth, in some places. So you could also, not the absence of gravity for sure, but you could, the temperature cycles and so on, you could simulate those.
So again, and this shows maybe my lack of understanding of the environments, but the materials that you're using and that you're testing here are readily available on Earth. When you go to run these processes on Mars, are they also available there where they can be mined and extrapolated from Mars, or is that something that has to go on the journey to Mars?
So we work with different mixtures. So we have developed a mixture for Mars and a mixture for Earth. And the different mixtures actually depend on the availability of local materials, but also on the local conditions, so that they work. And so the idea is that we make a material with what's available locally, and it works well locally. So we have different mixes, and the mix for Mars, we use materials that we know from previous NASA missions that are available on Mars, and we developed a concrete that out of Martian materials. It just happens that the materials that are available there are also available on Earth. So you could actually use the same mix in some conditions. One of the conditions is the low temperature, because the mix that we develop for Mars sets very fast on Earth on the usual temperatures above 0 degrees. But if you go below 0, it actually sets at the right pace. So it's interesting how a research for Mars end up discovering a material that can also work well on Earth. And the ecological footprint of this material is much lower than traditional Portland cement concrete. So it's a type of concrete that's called geopolymer. It's a different type of concrete.
So can you talk a little bit about the 3D printers? And we saw their ability to lay the concrete. We saw their ability to put windows in the structures, but do they also have the ability to do some of the mechanical functions, the electricity, the plumbing, all the other aspects that go into producing the dwellings?
Right. So for the competition, we had to develop an animation simulating the construction on Mars and show how you could place windows and how you could place electrical systems. Right. So I don't have this time to show that animation now, but I can briefly describe what it does. So basically, we have a robot that prints the structure. We have another robot that places the windows while printing. And we would have also robots that would place the other installations. So on the first step, so it basically places the ducts, the pipes. And on the other one, and the third level, the third stage, you would have smaller printers that we use to print the furniture, to print the finishings inside the shelter, and take care of the installations.
A question that's come in is the potential advantages are being discussed of possibly gained by deploying nanotechnology in the process.
So I have to be honest, we have not explored that yet, but probably in the future we'll come across some of the possibilities offered by nanotechnology.
Yeah. So it seems like some of the audience are having some of the same struggles that I'm having, and kind of wrapping my mind around how do you get everything from Earth to Mars, right? To do the kind of construction. So questions come in. Do you actually take smaller 3D printers that then print the larger 3D printers, or talk about on Earth we call it supply chain, right?
Right.
Supply chain look like?
So part of the score during the competition was attached to this issue. So the more materials we use that were available on Mars, the higher the score. So that's why we developed a concrete mix out of materials available on Mars, so that we do not have to carry them from Earth, which would be very expensive.
Right.
The same thing with the printer. So the printer that we designed is a printer that needs to be shipped on Mars. But it's fairly, I would not say it's lightweight, but it's not as heavy as one could imagine. So it could be shipped on Mars. And the idea is that you're going to have a kind of a dome structure to be able to print in a sealed environment. So you could control atmospheric pressure, for instance, while printing. So you could control the properties of concrete while being printed.
Yeah. So this is a fascinating topic. Talk a little bit about what's on the horizon in terms of the next competition that you're going to be participating in. Do you have the details of that, or does the challenge stay consistent year over year?
So we don't know what's going to happen next because NASA has not announced yet. We did participate in some meetings where they talked about the next steps. And the idea is that the teams who were more successful in the previous levels of the competition would actually help frame the competition in the next steps. So we were told that we might shift from Mars to the Moon. So the Moon will be, the goal of the next steps of the competition, just because it's closer to Earth. It's, probably easier to get there than to Mars. And that's all I know. So I don't know when it's going to happen. Maybe next year it will restart again. And in the meantime, our concern is actually to use the technology to help solve problems on Earth. So we are actually dealing with construction companies, trying to transfer the technology to them and so on. So we are not stopped waiting for the next stage of the competition. We're actually working for Earth.
So a lot of this was developed with the competition in mind, but think about the practical applications in terms of actually inhabiting the Moon or other planets. Do you think that that's going to be, will that be government sponsored like it has traditionally been through NASA and space exploration, or do you think it's going to be private companies that will start to move into this space? Like we just saw SpaceX take off and go and just dock with the space station. Where do you think the funding for this kind of exploration is going to come from?
I think a big chunk of it will have to come from the government because there are high risks involved, and so I think in that case we need to convince people that's worth investing. And I think this competition has already shown that, because the amount of money that was invested in the competition by NASA, produced fruits that are good, for Earth as well. So, that's one way of funding it. So you make an investment, you develop a technology, but the technology is not just to do something on Mars or, in another planet. It's worth for solving problems on Earth. So I think that's a strategy that NASA has been using, and I think that has worked quite well, at least in our case. But I think, at some point, when the technology is a little bit more mature, I think there'll be private companies interested in continuing the investment. And so I think we'll have a mix of both government, public funding and private funding.
So I can go in a couple different directions. You talked a little earlier about kind of the ethics that are involved in all this. So let's start here on Earth in terms of the ethics of kind of our responsibility to Earth and our carbon footprint and using these applications here. Is it positive or negative impact on construction practices in terms of how they have an impact on the carbon footprint?
I think that has a very positive impact in different ways. For instance, one was the material that we developed. It has a lower ecological footprint. So it consumes less energy and it produces less CO2 to produce. So I'm talking about the geopolymer concrete. So it's more ecologically friendly than the traditional Portland cement concrete. And the other one is how you design and operate the buildings. So because the design is optimized for the environment, and the idea is that use as less materials as possible, that it consumes as less energy as possible. So the design is optimized to minimize the use of resources. So what I'm trying to say is the technology that we are using to work in such a harsh environment actually, has a strong impact on what we do here on Earth, because we developed the technology and that it can be used here as well.
Yeah. So the other side of the ethics question then goes to when we leave Earth's atmosphere and start to build things on other things beyond, right? Whether it's the moon, whether it's Mars. What the way we would talk about it here on Earth would be the geopolitical ramifications, right? Are these partnerships with other countries? Are these United States alone and kind of looking for what the next frontier is in terms of, how do you think about this as a scientist?
Well, look, the team, we are based in the US because here we have the right conditions to develop this work. I think, American universities and Penn State in particular is very good at creating those conditions. So I don't think this could happen anywhere. So you need a special environment that we can find here. But look at the team. We have a team of people from many different places. Some are Americans were born in the US, some are Americans were born somewhere else. Some, like myself, I'm not an American citizen yet. I have a green card. So it's a very diverse team of people, not just in terms of expertise and background, but I think that's very important because when people who are brought up in different conditions, they will bring knowledge, from that context. And that gives you a richness and a diversity of approaches, which I think is very important when you try to solve hard problems. For instance, I think, some of the most thrilling moments of participating in the competition actually were our meetings. We said, okay, we have this problem to solve, and everybody starts, suggesting solutions. Some of them I would never think about because, they come from something that I was not exposed to in my past, but someone else was. So I guess, multidisciplinary, people with different backgrounds, with different profiles is very important. Different expertise, architects, artists, engineers, scientists, all working together. And because this is such a big endeavor, at the end, I think we need to involve, other countries as well. Obviously, like with any technology, there are risks. Technology can be misused, but that has never prevented the development of technology. We just need to be very careful with whom we share the technology. So we need to, keep an eye. We don't want the technology to go into the wrong hands, for sure.
Yeah, there's two ways to get to what's next, right? There's the competitive way, which we saw in the 60s, right? The race to space. But there's also the collaborative way, and that everybody kind of sharing information to solve the big problem. And it sounds like that's the approach that you have taken. Minds from all around the world coming to Penn State to solve a big problem.
Right. I think, collaboration is the key issue. I think we need to change the paradigm of our society. It has been based on competition, and there was a good reason for that, and it produced its fruits. So it was, useful. But right now, I think it's time to change the paradigm. So going from competition to collaboration, and you need to change your mindset, frame of mind to be able to do the shift. But I think it's very important, really very important.
So questions coming in about the actual competition. Where was it held? How many schools participate?
So the competition started with 82 teams, and at the end, only 2 survived. So Penn State was one. The other one was actually a private. It was not a university. It was a private company. So 82 down to 2 at the end. And the last stage of the competition was held in Peoria, Illinois. And actually we drove there. So we had to drive, that's why that actually, the competition was very well framed. So we had to find a way to ship all our equipment to a place that was 15 hours away. So we had to design for that as well.
So if people are interested, as we wrap up here, if people are interested in learning more about the work that you're doing, where would you direct them to go find that information?
So we are in the process of creating a website. In the meantime, there's some information on YouTube. So if you search for Penn State then at Mars, and the at is actually AT, not the symbol, you'll find some of our videos, and our videos have some interesting information. At least I think they are, entertaining, and they explain some of the technology.
That's great. Well, that's all the time that we have for today. Thank you, Professor Duarte, for sharing what is a fascinating topic. I know we can probably talk for another couple hours about all the aspects of this, but I want to really thank you for joining us and for sharing the good work that you're doing. And thanks to all of you on Zoom and on Facebook Live that have tuned in to today's virtual speaker session. As a reminder, we'll be hosting additional speaker sessions in the coming weeks, and you can find out more information about that on our website at alumni.psu.edu. Thanks again for all you do for the university, for the glory, and for the future. We are
Penn State.
Excellent. All right.